Okay, dear students, today's topic is on stiffness method, and we have to analyze a frame, space frame using this method. This is very important because this is included in your final term exam. And one thing more, that I'm not gonna solve it completely. Rather, I'll be leaving this some part of it, and that would be part of your final term exam. The thing is, I'm gonna give you some idea in this lecture about how to start a method, a stiffness. How to start this question, and then again, in the next lecture, I'm gonna tell you how to develop or construct a stiffness matrix, and that would be a complex structure. However, this question would remain unsolved, and that would be part of your final term exam. I'll be changing some loads. The geometry, basic geometry, number of spans would remain same. All other data would remain same. Only the loading would be changed in the final term exam. So I'll be telling you. Okay, the first step is you should know that if you have to solve this on the flexibility method, you have to find the SI. And SI is 6m plus r minus 6j. Number of members, I have 3. Support reactions, I have 18 minus joints 1 2 3 4. So it comes out to be 18, and 18 minus 24 gives us minus 6, and minus 6 plus 18, 12. And if I have to solve it on using stiffness method, I have to find its Ki, that would be equal to 6j minus r. Number of joints I have 4, support reaction I have 18, 6, 6, 6. So it comes out to be 6 degree. So you have the choice to solve for, if you have the choice for to solve it on flexibility and stiffness. Here we have no choice. You should prefer this method, stiffness, because our Ki is very less. Second thing is, for example, you have a plane frame, and the Ki in this case would be equal to 3j minus r, and number of joint we have 4, support reaction we have 3, 3, 6, and it comes out to be 6 degree. So our Ki is 6 degree. But this Ki can further be reduced if I am provided a condition that ignores axial deformations. So for this column, this is axial deformation. For this column, this is axial deformation. This is one beam and it has 2 axial deformations. So one can be removed. The other would become sway. So in total, it has got 3 members. So 6 minus 3 gives us 3 degree. It means its Ki can be reduced to 3 degree. Here again, in this case, I have 6 degree of freedom at this point, and these have been represented here. Because this is fixed, so there would be no degree of freedom. All degree of freedom lie here: D1, D2, D3, D4, D5, D6. This is axial deformation. This is moment degree of freedom. This is moment degree of freedom. This is axial deformation. In total, there are 6. So these are arbitrary. You can call it D2, you can call it D3. Directions are arbitrary as well. It can be your directions, it can be inward, it can be outward, it can be any direction. So it's up to you. However, I have 6 axial deformations, 6 kinematic degree of freedoms, but you should know that D1, D3 and D5 are 3 axial deformations. You can imagine D1 here, D5 here, and D3 here. Now D1 is axial deformation for this, D5 is axial deformation for this, D3 is axial deformation for this beam. So 6 minus 3 can gives us 3 degree, and it would become very easy. But the thing is, this instruction has not been provided, that I have to ignore the axial deformation. So I cannot ignore the axial deformation. So I'll have to take the whole degree of freedom, that is 6 degree, Moreover, this data has been provided. These are flexural rigidity in each direction, so it cannot be ignored. Now, so it's become very easy. So I have got this d is equal to d1, d2, d3, d4, d5. These are all degree of freedom at this point, so I cannot ignore the axial deformation. Okay, next step in this stiffness method. For example, I have this beam, and this beam is like this, and I have to solve this beam on stiffness method. So I have 1 degree of freedom here. So in this, so d is equal to d1. As there is no moment here or no applied moment here, so there is no ED. So here there is no ED as well, because there is no load on the joint, this joint B. There is no applied moment here, so Adl matrix is 0. Okay, Adl matrix is again the fixed end moments. So you convert it like this, and for example, I have load here. So that would be, first that would be anti-clockwise, this would be clockwise, this would be anti-clockwise, this would be clockwise. And for example, if I have a point load lying or resting on the midpoint, then it would be PL by 8 and PL by 8. And what if this P load is resting at a distance A from left and B from right, then this would be equal to PB square A by L square, and this would be equal to PA square B by L square. And what if you have UDLs, W, and this is L, then this would be equal to WL square by 12, this would be equal to WL square by 12. So it's very easy from your basic BSc knowledge. So I have to find the Adl matrix here as well. For this, as it is resting on the center point, 10 feet from the left, 10 feet from the right. So this is PL by 8. So first you have to assume it. This is Y, this is X, so Z moment would be formed. This is counterclockwise. As I told you, from the left, if you are going to start, this should be anti and this should be clock. So this is anti and this is clock, PL by 8. Here it is at a distance of 10 and 15. The formula would be this, I have told you. Again, this is anti and this is clock. And based on these directions, I have applied the loads as well. But 10 kip, you can find the load 5 and 5. This is 20, you can find load 12 and 8. So I mean, you are just balancing it. Adl matrix is highly dependent upon this matrix. I mean, for example, this is D1 and this is axial deformation in X direction. So here I have got no axial deformation or no load here. So Adl1 is 0. This is D2 is actually this moment in X direction. So here at this joint I have 72 kip foot. In the same direction as of D2, so this is 72. D3 is this, and D4 is again moment here. I have no D3, 0, D4 is same, 25 kip foot, 25 kip foot. I have to consider all the loads and moments here, not anywhere else. D5, vertical load or vertical deformation, it's 12 plus 5, 17. D6, no moment here, so D6 is 0. Next, AM matrix is very important and it depends upon you. I am calling this as member action 1, and you at least, I mean, it's your job, and it can be, there can be numerous values here, but you should go for at least 6 per joint or 6 per support values. I mean, I call it 1, this is call it 3, this is, I call this 4, I call this 5, and I call this 6. So 6 and 6 and 6. So there can be 18 elements here, and there should be 18 elements. At the end you would be able to calculate these reactions, support reaction, without much. I mean, it has to be a matrix and it can be easily solved on Excel. So this is member actions and it does not depend upon D or AD matrix, unlike Adl matrix. Now, stiffness matrix, as we know, there are 6 degrees of freedom here. So the order would be S6 cross 6. So you have to develop this and this is your job, but I am going to develop it for one case. I am developing it for D2 is equal to 1, and you know what D2 is. D2 is actually a moment degree of freedom at point B in X direction. So in the next lecture, I am going to explain how to develop a stiffness matrix in detail. So this question would remain unsolved and that would be the part of your final term exam. Okay, first of all, you should know what D2 is. D2 is actually a moment in X direction here, this. So the thing is, you should remember or recall that, for example, you have this beam and this is 1 degree of freedom. So here the degree of freedom, I have to give it rotation, and that rotation would be like this, clockwise, and as a result moment would be produced clockwise, 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 and the magnitude would be equal to 4 EI by L, 4 EI by L, 2 EI by L. Now consider this is clockwise, the load would be anti-clockwise. I mean, it should form an anti-clockwise moment here. Anti-resistive is clock, balance it with here, and same would be here. So I'm gonna do it same for this. I'm gonna give this joint a rotation or moment in this direction, in X direction. As a result, in the shoulder members, that is beam and a column, moment would be produced. So magnitude at the near end is 4 EI by L, 4 EI by L. Remember, when you are giving it a rotation, so this is a near end and the magnitude of the moment is 4 EI by L, 4 EI by L. And here it would be clockwise, but the magnitude would be equal to 2 EI by L. For example, this, and you are applying a clockwise rotation, a clockwise moment here. So clockwise and clockwise, 4 EI by L, 4 EI by L. This would be equal to 2 EI by L. This would be equal to thing is, I am rotating this joint in this direction. So as a result, the moments are produced here, and that would be equal to 4 EI by L. As it's a moment in X direction, so this is 4 EIX. So I have to take the value of EIX because the moment is in the X direction. 8. So that would be equal to 4 into 8. This span length is 15, probably 25. So this is not 15 by, this is 25. So you can correct it. This is 25. I'm gonna correct it. This is 15. I mean, this is wrong. So I'm gonna correct it once for all, so that this would be the part of the change should be permanent. So it is 25. Okay, so I'll make it permanent. How? I'll keep this. Okay, this has been kept, so it is 25 now. This is actually 10 plus 15. 10 and 15, so it's 25. So it's now permanent, 25. So 4 EI by L, it is equal to 4 into 8, where it comes out to be 1.28, half 0.64, 2 EI by L. There would be a vertical reaction here, and that vertical reaction should form a clockwise moment here, clockwise. As a result, anti-clockwise moment has been resulted, and its magnitude would be equal to 6 EI by L square. Again, EIX value would be used because all the moments are in x direction. Similarly here in this column 4EIX by L, again the L values would be the length of the column. 2EX by L, the length of the column 15 would be used. Okay, this is y, this is moment in x, so there would be a load in z direction. And it should be in this direction because it is forming a clockwise moment here, so anti-clockwise is applied. This would be counterbalanced with this. So if this is in this direction, apply it in opposite direction. And its magnitude is 6EIX by L square because moments are in x direction. This is very important because the shoulder moments have been produced, but as you are rotating this joint B, as a result, torsion would be produced here. And the magnitude of the torsion would be equal to always Gj by L. Gj is given 5 and this is 20. So 0.25, and this would be resisted here as 0.25. So it's very easy. So I mean, it does look complex, but it's very easy, and I'm gonna explain it in detail in the coming lecture how to develop the flexibility method. Finally, I have to, as this is, I have applied D2 is equal to 1. So all the values here would be 2, 2, 2, 2, 2. S1 is actually, what is S1? Recall as D1, and this was D2. So S12 as, so this is, there is no point, this is easy, 2, 2, 2. S12 would be all loads in this direction, x direction. So I don't have any load in this direction, so it is 0. S22, as this is D2 is a moment, so all the moments in this direction would be S22. Now you can see this moment, and this moment. This would be added. S32, what is S32? If you recall S3 is load in this direction or axial deformation in direction, as D4 is moment in this direction. So I mean S32, I have this, you should remember this is 3, D3, and this is D4. D3 is actually a load in this direction or axial deformation in this direction, that is Z. So I have got 0.2133 at this point. No moment in this direction, so that's why S4 is 0. So what was S5 and S6? S5 vertical and S6 vertical. So I mean D5 is this and D6 is this. So I have got one vertical load here, 0.076. So that D5, I have to remember this, D5 is just vertical, D5. So I have got this load here. This is wrong. This should be 0.0. So let me clear it. This is 0.076. Why I have written this 0.0768? Because this is along D5. So I am going to save it. So it's saved now. I mean, there can be mistakes, but actually D6 too is 0 because this is D5. D5 is actually the vertical deflection and D6 is moment. So I have mistakenly done something. Actually S62 should be 0 because D5 does exist. This is vertical, so this should be 0. So this should be 0 because there is no moment in vertical direction here. No moment is there in vertical direction corresponding to D6. D6 would be the moment here. So there is no moment here. So it should be 0. So let me find it, and now I'll do this. Okay, this. So it would be 0. this is 0. So it's very easy. I mean, now it has been corrected. It's very easy. You have to solve it, and I'll be giving it now. I mean, I'll be giving you in the final term exam. But this concept is very important. This concept is very important, and in the next lecture, in the lecture 14, I'll explain you in detail how to develop the stiffness matrix. So we'll be done with this method. The prime aim of this lecture was to educate you on the development of D and Adl matrix and these things. These are flexural rigidities in 3 axes. It means the cross sections are not similar for beam 1, beam 2 and column. So that's why we have got 3 values for EIZ, EY and EIX. And remember, I have to put all EIX value here. Why I have to put all EX values here? Because all the moments are in X direction. Therefore, I have applied all EIX value here. Secondly, this is axial rigidity. I mean, you must have studied this formula or this term for trusses, but it also holds true for frames. I mean, when you would apply D1 here, I haven't applied D1 yet, so its magnitude would be equal to EA by L. For example, I am applying D1 here, so its magnitude would be equal to EA by L. Similarly, if you apply a moment here at this joint, then a torsion would be produced here, and that would be equal to GJ by L. So the thing is, if I am pulling it axially, axial deformation would be produced here, and that would be EA by L, and that would be resisted by this fixed support here, EA by L, and here it would be resisted as GJ by L. So this is very important. These properties are these values are very important, and these would be incorporated in our design. So thank you very much. I mean, I'll try to post the other lecture now or tomorrow, and then we'll be able to study about we'll be able to know how to construct the stiffness matrix for a complex structure.